2. It's pretty simple, so hopefully everybody's done. Okay, so the goal of this is to figure out the mass of our model that will give us dynamic similarity to the meteor. So first, here are the 3 dimensionless groups that we have to work with. The first thing we'll realize is that since we want to find mass, this first dimensionless group is not going to hold any information. We already know both of these things, so we're not going to be able to get any more information out of this group. So you don't need to pay attention to that one. Secondly, we're not given any information about the crater volume, so we can't use this dimensionless group. So this is also out of the running. So we're going to focus on this one right here. All right, so for our model to be a good estimate for the meteor, we want these 2 dimensionless groups to be equal. And we know almost all of these parameters, so we can just solve for the mass of the model. And then we can substitute in values. Notice that we don't need to know the density of the model. We know that it's 2 times that of the meteor, so we can just take this quantity and substitute in 2. Additionally, we don't actually need to know what the acceleration we achieve. We just know it's 500 times greater than the gravity in the meteor. So instead of actually calculating values out, then you might have extra error there. Just go ahead and put like 2 and 1 over 500. It'll save yourself some time, save yourself a step that you may make a mistake in. So this is just a lot easier and a lot quicker. And then you end up with 1.5 times 10 to the negative 3 kilograms, which is pretty small and definitely feasible for a small scale model. All right, so that was the solution to this. So let's go back to that second group and just check to make sure that this is going to be reasonable too. We'll see what kind of crater volume we're going to get out of our model. So we can solve for the crater volume of the model. And let's just, as an order of magnitude estimate, pick this as 1 kilometer squared, which is pretty big. It's about double the meteor volume. Probably be bigger than that with a huge meteor crashing from space, but as an order of magnitude estimate, just to give us some sort of picture, let's use 1 kilometer cubed. And we see that our crater, our model crater, will produce about a 1/10 meter crater volume, which is pretty good. Right? It's reasonable. It's something we can analyze. It's consistent with the scale of our model. So this model should prove pretty effective for modeling an actual meteor. This wasn't part of the problem, but just some further analysis you could do with it. All right, any questions on this?